Welcome to a new episode of my exercise series Introduction to Physics. Today we are going to talk about electric fields, and in particular we will focus on plate capacitors. What are plate capacitors? Basically, a plate capacitor consists of two parallel plates, mostly in a vacuum. It represents a deflection system for an electron beam. And in today's task, we will focus on a single electron. This single electron enters the field between the plates at a speed of V0 equals 1.6 times 10 to the power of 7 meters per second, perpendicular to the field. The plates have a distance of 4 centimeters and a plate length of 10 centimeters. Calculate the speed at which the electron emerges from the capacitor field if the applied voltage is U equals 300 volt, and B, calculate the vertical distance h from the original direction of movement. For a better understanding, let's make a little sketch first. You can see here the two plates. The upper plate in black is charged negatively, and the lower plate, also in black, has a positive charge. In between the two plates, we have the electric field, and it can be assumed if the plates are parallel and large enough that in between the plates the electric field is homogeneous. This enables us to do a relatively simple calculation. In addition, we have on the left-hand side our electron, and it travels at a velocity of v0 and hits the field perpendicular to the field itself. Yes, but it travels parallel to the plates before it enters the field. You can see this blue curve that shows the direction of motion, the path that the electron travels. And apparently this changes, which is simply due to the fact that the electron has also a negative charge. So regarding the upper plate, which also has a negative charge, there is a repulsion force, whereas the electron is drawn to the lower plate. And you can see that in the end, the electron will have a velocity v that we actually are supposed to calculate, and spoilers, it's going to be different from v0. And in addition, it leaves the field closer to the lower plate, so there is a clear vertical distance between original direction of motion and the place where we are leaving the field. So what values are given and what are we really looking for? We have given the initial velocity v0 as 1.6 times 10 to the power of 7 meters per second. In addition, we know that the distance between the plates is 4 centimeters and the plates have a length of 10 centimeters. Now, centimeter is not the basic unit, so let's divide both values by 100 and we get that the distance is 0.04 meters and the length is 0.1 meter. In addition, we have given the voltage of the plate capacitor, which is 300 volt. And we are searching for, first of all, the velocity of the electron when it leaves the field and this vertical distance. So how do we approach this problem? Well, we know that the electron travels perpendicular to the field before it enters the field. And the interesting thing to note is that in this horizontal direction, or let's say in this x direction, there is a uniform motion because in this direction there is no force pulling or pushing at the electron. So a uniform motion, yes, this means that it travels at a constant velocity regarding the horizontal direction. So at any point of the blue curve that we've just seen, there is a horizontal velocity, a horizontal component of the velocity, which is always the same. It's constant, so Vx is always equal to V0. What about the vertical direction, the y direction? In y direction we have the electric field, and this gives us an acceleration. So we have an evenly accelerated motion. And for any evenly accelerated motion, we know we have to take the acceleration into account such that the velocity v in y direction equals a times t. But what are a and t? Yes, a is the acceleration and t is the time. But apart from that, what in detail are they and how can we calculate them? Well, we know in general that whenever a force pulls on an object of mass m, we can write them down as F equals m times a. So we can actually calculate the acceleration of our object if we know the mass, and since it's an electron, the mass is a constant. So the only thing that we need to know is the force F. Where do we get this one from? Well, from the field actually, because we know in addition that of an electric field, the force that's pulling on a charge is the charge itself. In our case, it's not, any charge, but the charge of an electron, this lowercase e, multiplied with the uppercase E from the electric field. Because we know that those two forces are, of course, identical. It's the same force. So m multiplied with a equals e multiplied with the uppercase E. Yes, we can calculate the acceleration if we know the charge, the lowercase e, the mass, m, both constants, and we need to know the uppercase E. But this is not too complicated, since we are talking about a plate capacitor with parallel plates, and E then simply comes from U divided by D. And we can take all of this into consideration, and what we get is that the acceleration A equals E, the charge, multiplied with the voltage U, divided by M and D. D was the distance between the plates. And all of them are either constants or we had them given. So we can take them in their basic units, put them into this equation and directly calculate the acceleration. And what we get is that the acceleration of the electron is 1.32 times 10 to the power of 15 meters per second squared. This was the first part. In addition, we wanted to know about the time t that the electron needs to travel through the field. How can we get this one? Well, we know already that the electron travels the length of the capacitor uniformly at a constant velocity. But wait, a constant velocity is always really easy to calculate, because an object that travels at a constant velocity can be calculated as the change in distance divided by the change in time. So it's always distance over time. And in our case, it means that we have Vx equals L, the length, divided by time t. From this we can actually get t, because Vx, remember we said it's a uniform motion at any point of our curve. This horizontal component of the velocity is always identical. And it's identical to the initial velocity. So it's basically V0 equals L divided by t. And hence time t equals L divided by V0. And since L and V0 were given, and if we take them in their basic units, we get that the electron needs the time of 6.25 times 10 to the power of minus 9 seconds. So a really short time span. But that's all we needed, right? Because we wanted to calculate the velocity in vertical direction, Vy, as the product of a and t. And since we've just calculated a and t, we can derive Vy directly, and we get that it's equal to 8.25 times 10 to the power of 6 meters per second. wait, now we have two different velocities. We have the horizontal velocity and the vertical velocity at the end of the field. How do we combine them? Because our electron is apparently traveling with, one velocity. In order to get a resulting velocity, we need to know about superposition. Superposition means that we have an undisturbed superimposition of the motions. It means that, yes, in horizontal direction, we have our uniform motion, whereas in vertical direction, we have an evenly accelerated motion. But those two different kinds of motions on the same object do not influence one another. So we can derive the velocity v as the square root of vx squared plus vy squared. And what we get is that the final velocity is 1.8 times 10 to the power of 7 meters per second. And yes, as promised, the initial velocity was 1.6 times 10 to the power of 7 meters per second. So really v in the end is different from the initial v0. Are we done? No. There was another thing that we wanted to know. We wanted to know in addition how large is the vertical distance in the end from the original direction of the movement. But this is not too complicated now, since we basically have everything we need. We know that this is a problem in vertical direction, in y direction. And in this direction, we have an evenly accelerated motion. So we can write down the equation of motion that relates the distance traveled to the time. And in our case, the distance that it travels in vertical direction is this height h that we are looking for. And it's always equal to a divided by 2 multiplied with the time t squared. And here also, we have already calculated a and t. So we can take them, put them into this equation, and we get that the height difference is 0.0258 meters. Or let's put it like this, it's 2.58 centimeters. And yes, a little comparison shows that this value is of course smaller than d, the distance between the plates. And I suppose this actually makes sense if you think about it, because if it would, in theory, travel further than the distance, it would have been hitting the positive plate and not been getting out of the field. So yes, it actually makes sense. And that's it already for today. I hope this really helps you understand this kind of problems a bit better. And if it did, consider subscribing, give me a thumbs up. And if you still have some questions, leave them in the comments below. And I hope to see you soon for another video. Bye!